Good afternoon and welcome to this Knowledge Insight series session. Let me introduce myself. My name is Preetha. I am a postgraduate with a specialization in statistics. Currently, I am working as a data science associate in an organization called Grid Analytics India Private Limited. Today, I will be talking about data transformation, how data transformation made easy for non-normal to normal data. Before getting started, let me give you a brief introduction about the data transformation. So this is the basic introduction to data normality. So normality is a common assumption in statistical analysis for most parametric tests. Again, normality in regression refers to the error distribution, means when we do linear regression, the error should always follow the norm. So when our data is not normal, this data non-normality issue is fixed by applying the transformation. The transforming data is a method of changing that distribution by applying a mathematical function to each data value. So there are three types of transformation will be discussed in this session. The most commonly and widely used data transformation techniques are namely log transformation, Box-Cox transformation, and the Johnson-Esue transformation. So log transformation is just a way to change the data that has very large number or very small numbers or has skewed type of curve. It works by taking the logarithm of each number in the data, which makes the data more symmetrical or normal shaped and reducing the effect of extreme values or outliers. So let us first check the log transformation with the help of Statistica first, a visual data science platform with no code and the low code capabilities. So for log transformation, we have characteristics dataset, which is an inbuilt dataset from Statistica. So we have in total 12 variables. So suppose the fourth variable height. So we want to check whether this height variable is normal or not. Then we will apply the log transformation and we'll be checking that whether this data after transformation becomes normal or not. So first, from the node browser, we will have the transformations of variables. Next, in the transformation of variable, we will simply write let us first make a new column here. So all the transformed variable will be written in the 13th column. I have made the new column as V13 and we want to transform our height variable which is listed in the column 4. So that is V4. Next OK. Yes. Next OK. Now if I run the node, it will produce me the new data set with another new variable. Next, I will be checking whether this new transformed variable is normal or not. So for that, I took a histogram. Next, in the histogram, I will be taking the new variable, then OK. In the advanced section, I will be checking the Shapiro-Wilk test, then OK. Then if I run this node, it is giving that even after the log transformation, p-value is less than 0.05. So log transformation here is not working. So again I am going to the slides. So there are three kinds of transformation. So if log transformation is not working, the next most popularly used transformation is Box-Cox transformation. So Box-Cox transformation is a set of power transformations. It made to stabilize variance and make data more normally distributed. This is required in many parametric tests and regression. This is the basic mathematical definition of the Box-Cox transformation. The main constraints of a Box-Cox transformation is the variable which you want to transform should always be positive. Means Box-Cox cannot handle negative value. And lambda is the transformation parameter, and this lambda is chosen by maximum likelihood estimation. So let's see how the Box-Cox transformation works in Statistica. Again, we will be using same characteristics dataset. So we will first delete the variables. So in order to write the formula, we need to know the formula. So here in the Statistica, we will get the formula easily. In the data section, Box-Cox, variables. Suppose we want to again transform the height variables, then OK. Keeping all the options as it is. Next, summary. So here we are getting ready to get lambda, which is 3.54, and formula for Box-Cox transformation is this. V4 means height to the power lambda 3.54 minus 1 divided by lambda 3.54. So we will copy the formula. Next, we will again go to the workspace. In this batch transformation formulas where we write the formula, we will make here another new variable. Next, we will paste the formula here. Here V4 will be capital. Next, OK. Then yes, then OK. Next, we can see the transform variable has been prepared in the column 13. Next, we will check whether the new variable that or the transform variable is normal or not. For that, again, we will be checking it through the histogram. Next, in advanced, the Shapiro will test and OK. Then if I run the code, here we can see the p-value is greater than 0.05. So our data is now normal. So after applying the Box-Cox transformation, the data is showing normal. Next, another popularly known transformation technique is the Johnson transformation. The purpose is same, that it stabilizes the variance and make data normal. So it is an extension of Box-Cox transformation, but unlike Box-Cox, it handles both the positive and the negative values. And this is the mathematical definition of the Johnson SU. SU means when the data are unbounded. So here Y is our transformed variable, and gamma, delta, this is gamma plus delta. This is inverse hyperbolic sine function. within parenthesis x minus xi divided by lambda. This gamma, delta, xi and lambda all are parameters, and we find the best gamma, delta, xi and lambda parameter so that the left hand side y becomes normal distribution. And this operation is done through the maximum likelihood estimation. So for that, we will be again checking all the three transformation, namely Johnson, Box-Cox and the log transformation, now using the R node and the Python node of Statistica. So first, I will be using the same characteristics dataset for R. So first I will be accessing the input dataset. This is the command used. The first two command is the command used to upload any active dataset inside the workspace of Statistica. Next, I will be checking the exact names of columns. For that, I have written names df. Next, after taking the, as we have got the name of exact names of the column, next we will be taking the log transformation of height. Next, we will be checking the Shapiro test, the popularly known test of normality of log height. That whether the transformed variable is normal or not. Next, we will be calling a library called mass. It will is the calculation of maximum likelihood estimation for Box-Cox transformation for achieving the optimized lambda value. Next is the Box-Cox transformation. Now we will be estimating the lambda. Then we will be applying the transformation with the formula. Here is the formula that dataset from the dataset we have extracted height. So we want to apply the transformation in the height column. So height to the power lambda minus 1 divided by lambda, and lambda has already been achieved in the previous commands. Next we will be checking whether the after applying the Box-Cox transformation, the new variable is normal or not through Shapiro.test. Again, in the same node, I will be checking the Johnson transformation also. In the same way, the uploading the dataset, the checking the exact names of the column. Next, extraction of the heights column from the dataset, and the next column is for checking whether there are present any missing value or not. Next is the calculation. As I have shown the formula of the Johnson ACU density, I have written the formula. Next, the parameter estimation, that gamma, delta, xi and the lambda. Next, then calculating all the PDF and then fitting the parameters value. For the parameter estimation, the initial value has taken the 0. Next, after achieving the y, I mean the transformed value, we will be checking whether the transformed variable is normal or not, again through the Shapiro.test. Next, if I run the node, we can see that after the log transformation, the p-value is still less than 0.05. So after log transformation, our height variable again is not normal. Then after calling the library mass, then if I apply the Box-Cox transformation, so after applying the Box-Cox transformation, p-value becomes 0.09, which is greater than 0.05. So the after application of Box-Cox transformation, our height becomes normal. Next, after applying the Johnson density, we can see our p-value becomes much greater than 0.05. So height becomes now normal. Next, using the Python node within the Statistical's workspace interface, the first commands are written for that import warnings for warning messages, and the output will not be printed in the same dialog box. So warning messages will be someplace else. Next, the df is equal to active dataset is for acquiring the active data characteristics within the statisticals workspace. Next, I have uploaded the two libraries, NumPy as an NP and the SciPy. From SciPy libraries, I have imported stats. First, it will check the Shapiro-Wilk normality test on original height, and it will show it is not normal. Next, the log transformation will be taken on height, and then the transformed height, that is log of height, will be saved in the dataset df. Next, in the fourth step, again the normality will be checked on the transformed height. Next, in the fifth stage, Box-Cox transformation will be done, which requires positive values. And in order to check and make if there is any negative values present in the height column, we will convert all the negative value to the positive value. For that, we have written this command. Next, we will test the Box-Cox results by the Kolmogorov-Smirnov test, because Shapiro-Wilk test is sometimes become sensitive for the large samples, so it doesn't give us good results. And there is also lambda present, so we use here KS test, another test for the normality checking. So if the case results p-value greater than 0.05, it will print the data are approximately normal, and if not, then it will print that it deviates from normality case test. Now, if we run this node, it will produce that after log transformation, it is written in the output that p-value is 0.008, which is much smaller than 0.05. But after the Box-Cox transformation, when we take the Kolmogorov-Smirnov, the p-value becomes 0.296, means it is greater than 0.05. So after applying the Box-Cox transformation, the height column becomes normal. Next, we will be checking the Johnson's transformation. So same commands I have written for separating the warning messages and the outputs. Next, the same commands for acquiring the active dataset from the Statistica's workspace. Next, few libraries are required for the Johnson SU PDF calculation, namely pandas, numpy. From scipy.optimize, we import minimize. Scipy.stats, we imported Shapiro. And from math, we imported inverse hyperbolic sine function, square root, pi. Next, we have named the actual column as x, and we have checked whether there is any missing values or not. Next, the Johnson SU PDF calculation. We have written the exact formula within the code, then calculating the negative log likelihood function. Then in the next stage, we estimated the parameters, namely gamma, delta, xi, and the lambda. Next, it transformed to the normal scale, and then we check the normality test using the Shapiro.test. And okay, then if we run this node, it will produce a report document, it is also showing that after applying the Johnson SU transformations, our p-value is 0.1355, which is much larger than 0.05. So Johnson SU transformation is also an helpful technique for reducing non-normal distribution to normal distribution. Thank you.
Hello.
Yes, sir.
Okay. So you are done, Preetha?
Yes, sir.
Okay. Thank you. Thank you.